Alright, so in this video we're going to talk about basic gas laws. Our basic gas laws look at the relationships between pressure, volume, and temperature. The first is Boyle's law. We use Boyle's law to define the relationship between pressure and volume if the temperature and the amount of gas is held constant. If the volume of the container is increased, then the pressure is decreased because the particles have more space to move around. So if they have more space to move around, they're going to have less interactions. And if the volume of the container is decreased, then the pressure, of course, would be increased, because if you limit the space they have to move around, then they're going to collide more often, and those collisions are what create pressure. Boyle's law states that the pressure and volume are inversely proportional. That's when one goes up and the other goes down. And so the equation that we get from this relationship is P1V1 equals P2V2. Now, when we look at problems like this, our initial conditions are, on the left side here, are 1s, and our changing conditions, or our final conditions, are pressure, are the 2s on the right-hand side. Alright, so we're going to, in this first example problem, we have a sample of gas in a 2-liter container at a pressure of 740 millimeters of mercury. And so our initial pressure is 740 millimeters of mercury, and our initial volume is 2 liters. Alright, so what would be the new pressure if we reduce the volume to 1.25 liters? Now, what units we put in here does not matter as long as the unit of pressure on the left and the right are the same, and the unit of volume on the left and the right are the same. So since we have millimeters of mercury on the left, our answer for the pressure on the right is going to come out as millimeters of mercury. Now, we know from before that since we're decreasing our volume, that we should expect an increase in our pressure. So we'll know whether or not our answer makes sense based on knowing that relationship. And so to solve for P2, of course, we would divide by 1.25 liters. And since liters on top and bottom would cancel, that leaves us with our millimeters of mercury. And so we multiply 740 times 2, and we divide by 1.25, and we get 1184 millimeters of mercury. Now we have 3 significant figures here and 4 significant figures there, and 3 here, and so we need to round our answer to 3, so that would be 1180 millimeters of mercury for our final answer. Okay, so that's Boyle's law. Charles' law defines the relationship between volume and temperature. Now the temperature here must be in Kelvin, and to review, to convert to Kelvin, we take our Celsius temperature and we add 273 to get our Kelvin temperature. Okay. Now, if the pressure and the amount of particles are constant, then the temperature of the gas is increased, the volume will also increase. So in other words, if we increase the temperature, we get more motion, and the particles will be allowed to take up more space. If the temperature of the gas is decreased, then likewise the volume will also decrease. This is a direct relationship. So when one goes up, the other one also goes up. So if you picture particles flying around inside of a balloon, and you were to put the balloon in the freezer, the gas particles would slow down, and therefore they would not hit the balloon walls as hard, and the balloon would shrink in size. Okay? And so we get an equation from this, V1 volume over T1 equals V2 over T2. It's a direct relationship, so we're going to be dividing, whereas in the one before, with Boyle's law, we multiply. Alright, so let's put this into action. We have a gas that's collected and found to fill 2.85 liters at 25 degrees Celsius. So again, these are our initial conditions, our 1 values. So we'll have 2.85 liters over our temperature, which has to though be in Kelvin. So 25 plus 273 gives us 298 Kelvin. And then we get our what volume will be at standard temperature. Now standard temperature, if you recall, is 0 degrees Celsius, so in Kelvin that will be 273. Again, standard temperature is also listed in your reference packet. So we have 273 Kelvin in our unknown volume, V2. So to solve this, I would recommend doing a cross multiply to help you out with that. So we can cross multiply. We get 2.85 times 273, and then divided by 298. And we get that the volume then will be 2.61 liters. And again, we started with 3 significant figures, and so we end with 3 significant figures. Okay. So our next basic gas law is Gay-Lussac's law. And Gay-Lussac's law is the relationship between pressure and temperature when the volume and the amount of gas are held constant. So if the temperature of a container is increased, then the pressure is also increased. And if the pressure of the container is decreased, the pressure decreases. Okay? And so this is another example of a direct relationship, okay, where one goes up and so does the other. So if we think about this law, the gas particles are moving faster, and this is what happens when the temperature of the gas is increased. The force of impact will increase because they're moving more quickly. They're going to collide with more force, therefore having more pressure. And so the increase of temperature increases the pressure exerted by a gas. And so since this one is direct, it will look a lot like the previous one, only have pressure on top, so P1 over T1 equals P2 over T2. Would be Gay-Lussac's law. So for this example, we have 10 liters of a gas is found to exert 97.0 kilopascals at 25 degrees Celsius. What would be the required temperature in Celsius to change the pressure to standard pressure? Well, since we're looking at kPa, we have to think about what standard pressure is in kPa. If we look that up on our reference packet, we'll find that's 101.3. Alright, and so our initial pressure was 97 kilopascals. Our initial temperature, again, this has to be in Kelvin, so I had 273, would be 298. It's going to be equal to 101.3 kilopascals over our new temperature. Again, I recommend cross multiplying. So we get 298 times 101.3, and then we would divide by 97. And so for T2, we would get 311 Kelvin. The problem asked us to find that in Celsius, so we would then subtract 273, and our Celsius temperature would then be 38.0 degrees Celsius. Okay. Now here, this 10 liters did not matter because it did not change. It was held constant, and that's Gay-Lussac's law. Alright, so finally we're going to combine all of these concepts together. What happens when we change all 3 conditions, pressure, volume, and temperature? For that we get the combined gas law, and that is P1V1 over T1 equals P2V2 over T2. Now this one you'll find in your reference packet. And for this problem you can actually get all of the other 3 equations. So you don't actually have to memorize them. So let's say, for example, you wanted to look at Boyle's law, which holds temperature constant. If temperature is held constant, then both of these are the same value, and they cancel out. And so you would get Boyle's law, P1V1 equals P2V2. If we were holding our pressure constant, those would cancel out, and we would get V1 over T1 equals V2 over T2, which is Charles' law. And then if we held volume constant, we would have P1 over T1 equals P2 over T2, which is Gay-Lussac's law. So what you really need to know is the names of the laws, but you don't have to memorize all the different equations, because this one, which is in your reference packet, will give you all the others. Alright, so let's look at an example problem. We have 2 liters of a gas that is collected at 25 degrees Celsius and 745 millimeters of mercury. What is the volume STP? Again, STP, if you recall, stands for standard temperature and pressure. Standard temperature and pressure. Right? And the values are 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere, or 101.3 kilopascals, or 760 millimeters of mercury, or 760 torr. Right? All of those are standard pressure. Right? Alright, so you have to recognize that the 5 values given in the problem, and then you have only the 6th one as your unknown. So remember that the Celsius, of course, has to be in Kelvin. So our 25 degrees Celsius is actually 298 Kelvin. Right? And so sometimes it's helpful to organize all our information. So our initial pressure was 745 millimeters of mercury, and our initial volume was 2 liters. Our initial temperature was 298 Kelvin. Now, our new pressure is standard. Again, it doesn't matter the units, but they do need to match up on both sides. So since this one was in millimeters of mercury, let's use standard pressure in millimeters of mercury, 760. Right? Our volume is what we're looking for, so we'll call that X. And then our new temperature is standard temperature in Kelvin, is 273. So then let's plug all this into our equation. P1, 745, times V1, 2, over T1, 298, equals P2, 760, times V2, which we don't know, call that X, over 273. Again, I recommend using a cross multiply to solve our problem. So we get 745 times 2 times 273, and then we'll have divided by our 298 multiplied by 760. And we'll get 1.79605. If we look back at our significant figures, we have 3 here, 3 here, 4. So we're going to go with 3. So we have 1.796 would make 1.80 liters. Okay. Now, if you had trouble getting that and solving this equation, you may have put it into your calculator incorrectly. So it may be helpful to you to write out what you're doing when you do the cross multiply. And so you have to do your 273 times 745 times 2 that you're putting in your calculator equals 760 times 298 times X. Okay? And it may be helpful for some of you to go through and do the math out completely by hand if you're having trouble putting it into your calculator correctly. This will allow you to see really what you're doing and what you're putting into the calculator. And remember that this needs to be in parentheses of its own if you don't simplify that first. Okay? And you should still get 1.80 liters when you solve that.